Hello, welcome to this YouTube channel. It's a channel that deals with computational chemistry. And today we are going to be considering how to carry out DFT studies using Spartan. Basically, we'll be carrying out DFT study of small compounds. Now, the question you might ask yourself is why, first of all, what is DFT? Now, DFT means density functional theory model. That's the DFT model. It's a density functional theory. And this model actually uses electron density to determine the ground state properties of a many electron system. This is as opposed to other wave function systems that would try to track the electrons individually. So if you have a system that have a lot of electrons, instead of tracking the energy of each electron individually, the density functional theory model simply takes the electron density of that system. And the thing is that it's easier to get it and then it's faster. And then it uses this electron density to determine the energy of that system and other properties. Now, some of the applications of density functional theory is that it has been used to calculate molecular energies, that's the energy of molecules. And you will find a lot of research on this where they are calculating the total energy of a system, homo, lumo, and the rest. So it's used to calculate energies of molecular systems. We also use it to ascertain molecular structure. And lastly, it's often used to predict reaction mechanisms. And you might be asking yourself, why DFT? Now, the two strong points for DFT are accuracy and efficiency. Studies have shown that the density functional theory often get results that are reliable, results that are very close to that of experimental data. And that's why you will find that a lot of research use DFT. Now, secondly, is the issue of efficiency. Given that the DFT does not consider the electrons within a system individually, but considers the electron density, it's able to get the electron density faster and easier. Therefore, it will use less computational power and less computational time. So density functional theory is often used because it's accurate. The result agrees with what you have in experimental data, and then it uses less computational power, given that it's considering electron density rather than the individual energies of the electrons. Now, so today we'll be carrying out the density functional theory practical on two molecules. We're going to be considering methanol and then formaldehyde. So we're going to be using Spartan. So what I will do is I'll open Spartan. So if you've not installed Spartan, please, it's important that you install it now. Once you've opened Spartan, you will find Spartan is a graphical user interface application that allows you to carry out molecular modeling and several other things when it comes to computational chemistry. So the first thing to do is to model your compounds. Now there are two ways you can do that. To draw your compounds, you can use this. Yes, you can draw it here, or you can simply use the 3D form. So let's use the 2D. I always advise students to use 2D until you are very conversant with the structures and with drawing those structures, then you can always use 3D. But the first thing to do is 2D because that's what we are often exposed to. So I'll be drawing methanol. So methanol, that is, and then OH. Okay, so this is methanol. You can see that. So this is methanol. So, and then you can see the name there. So now let me take you here to still show you something. Now, when you draw your compound or your molecule using the 2D feature, it's often advisable that you clean up your structure. So I'll clean this up. So once you click on this, it cleans this, just it cleans it. Now then what you do is to click this, which will convert it into 3D. You can see that. So please don't forget, I have to go back to show you how to clean up your structure. It's not evident for methanol, but when you're drawing large structures, you'll see the advantage of cleaning up your structures. Now, what we can do is to save this. So I'll be saving this as methanol. Let me add DFT to it. Now, the next thing is to open a new space. Now, where I'll be drawing formaldehyde, or what we call methanol. So for methanol, you can still use this, and then so now if you know methanol, that is, now to have a double bond, and then O, so, and then you have I want this to be H. Good. Now, so let's clean this. Good. And then you can see it's this formaldehyde or methanol. Now you can choose to expand it, and then I'm expanding it. So this is methanol. Now the name is written here, formaldehyde. So what we want to do is to simply compare their energies to see which is stable and which is more reactive. So we save these two as formaldehyde, DFT. And let's go back to this. So we're going to work with this. That is methanol. So this is methanol. Now you can change this to see it in different ways. If you want to see it like this, you can see that. You can see it like this. You can simply change it to look like this. You can change it to look like this. Okay, so whatever model you choose. I often would like to work with not this, I often like to work with this. And also sometimes you can also choose to attach labels. So if you want to attach labels, this carbon 1, oxygen 1, hydrogen 4, you can choose to do that. But I will remove the labels now. So the first thing, like I showed you in the last video, is that when you want to carry out any computational work, it's important that your structure is representative of the structure that has the lowest energy. Often you would always have to do that, except you're working with other kind of calculations. So the first thing we do is to optimize this structure. And I showed you how to do that. Simply go to setup, calculations, equilibrium conformer. We often want to use molecular mechanics, and click on this, and you can simply submit. Good. Now it has completed. Good. So this structure we have is our equilibrium structure. It's our equilibrium conformer. I can even click on it to see that. You can see that. So it gives us the output and tells us that this is the lowest energy conformation, and that is the optimized structure. We're going to be doing the same for formaldehyde. So simply go to setup once more, go to calculations, equilibrium conformer, molecular mechanics, this, and then you can always vary this number. If you want it to be just 1000, to search from 1000 conformers, 100, depending on what you're working with. And so good. So it's completed. Beautiful. So the first thing we did was that we carried out what? Optimization to obtain the lowest energy conformer. Now the next thing is to carry out our DFT calculation. So what you do, go to setup, go to calculation, go to equilibrium geometry, please. The first one was equilibrium conformer. This is equilibrium geometry. Then choose the density functional. Now, I often choose this um, Becquerel and Parr functional. Yes, B3LYP. Now, the choice of this, the functional you'll be using is dependent on what you're working with. It's important that you consult literature and know the functional that will give you reliable results. I'm doing this because I know that for elements with atomic number 1 to 30, you can always use the Beckett 3 Liam functional. It's a hybrid functional that's been found to be reliable. However, if you are working with um, other kinds of compounds or compounds that will contain atoms beyond the atomic number or even certain kind of systems, it's important to choose the correct functional and correct basis set. Now the next thing is this. This is the basis set. I'm choosing this CH₃OH star as the basis set I would be working with. And then I want to carry this out in a vacuum. Remember, the choice of the functional and the choice of the basis set is something you should be very careful about. You must consult literature to make sure you're choosing the right thing. Now, so when you've done that, what we simply want to compute, we're not interested in infrared, Raman, NMR, UV visible, and structure activity relationship. We are just interested in calculating their energies. So I'll just check this and check this. Now, if you were interested in the infrared spectra of the molecule, then you check this. Now, so what I will do is I will just simply um, submit this. So DFT for methanol has started. After started. Now, I think you can also run this concurrently. So I will also do the same um, for this. So go to calculations, go to equilibrium geometry, go to density functional, choose this functional, then choose this basis set. I've told you the choice of this should be is very significant. You must choose a functional and a basis set that represents the kind of system you're working with. So click this, click on this, and then add also submit. Okay, wow, methanol has completed. Okay, now if you want to see if the process is ongoing, click on options and go to local monitor, and you see okay, only formaldehyde is on. So let's save this. Now you can see this is methanol. Now before we started, you would observe that this part was not checked, but once it's completed, you observe that these orbital energies is now activated. Good. Now what you do is, let's click on this. Now, so you see that it brings out a figure that shows you the HOMO and the LUMO. Now, in carrying out DFT, what we intend to look at today is the energy of these molecules, and what we are specific about is what is called the frontier molecular orbitals, which are the HOMO, you can see this, and then the LUMO of that system. Now, HOMO simply means the highest molecular orbital, while LUMO means the lowest unoccupied molecular orbital. Now, so we have the HOMO for this. Now, look at this. The HOMO for this system, that is methanol, is -7.2, while the LUMO is 2.0 electron volts. Now let's go to formaldehyde, and then let's see. We click on this. Now the HOMO is -7.3, and then the LUMO is minus 1.1. So first of all, let's see how we extract information when we are done carrying out a DFT study. Now, I used methanol and formaldehyde because I want to compare them. You can actually just work with one molecule and you just do the same thing. So let's check our output. Click on this output and you can see more information, um, what you carried out, geometry optimization, the basis set that was chosen, the multiplicity, and you can see several things that took place, the values of the different atoms you had, their charges. And then if you want to work with it, because a lot of times you might need this information to also explain the results you've gotten. So you can always go to the output and then you find it there. Now, if you need a more, if you need, okay, this output, I was looking at variables output. Okay, now we are not getting anything from this, but okay, let's go to the summary. Okay, good. Now, this is just a summary of all you did, and then you can just see that it gives you the energy and then tells you the solvation energy. Now, so the next thing you should do is to go to the spreadsheet, click on spreadsheet. Now then, simply click on add, name, formula that we're interested in, E-homo, E-lumo, because that's what we're working with today. I mean, we just molecular weight. Now, the energy, we want it to be in electron volts, and then we apply. Good. So you can see that what it does is that it tells us that the name of the compound is methanol. It gives us the formula, tells us the energy of the highest occupied molecular orbital, and tells us the energy of the lowest unoccupied molecular orbital. Now we'll also do the same for formaldehyde. So click on this, go to add, name, formula. Okay, we did not add energy for the other one. E-homo, lumo, and then we can simply apply and then okay. Now you can see this, good. So we also have a case where you have the name, you have the formula, you have the energy of the highest occupied molecular orbital, and you have the energy of the lowest unoccupied orbital. So what we can do is, okay, I think we should include the general energy of that system, so we can add, let's add this to it. Let's just add energy to it in electron volts. So let's apply it, good. So it has added it. So let's do the same for formaldehyde. And then let's still add energy. Then, okay, good. Now, so what I can do, what I often do is that I will copy this before copying it. So highlight it and then I will take it to an Excel file. So I will open an Excel file. So I would paste it here. So this is for methanol. Now let's also get the information for formaldehyde. Okay, good. Now, so we can see this is quite interesting. So we can see that E-homo for methanol is minus 7.2, illumo minus 7.31, illumo for both, you can see it. And then, okay, so I'll take this here. So I want this. Now, we did not extract molecular weight for formaldehyde, but we can always calculate that. Now, if you look at this, you observe something. Look at this. I think I can increase this. Good. So you can see that the energy, the total energy of methanol is minus 31,000, okay, minus 3,148.75 electron volt, while for formaldehyde you can see the value minus 3,115.72 electron volt. Now you must have known that the more negative the energy value, the more stable that compound is likely to be. So it's likely that methanol is more stable than formaldehyde. But one simple way I'd often also ascertain this is to use the eHomo and the illumo. So what I will do is I will extract this. Now remember, so I'll copy this and let's take it here. So remember, this is for methanol. This is for formaldehyde. Good. So remove this formaldehyde. So I would also want to remove. Okay, so let's remove these two. You should also know how to work with Excel. So formaldehyde. Now, so these are the compounds, and then this. Now, under the density functional theory, the difference between the HOMO and the LUMO gives us what is known as the HOMO-LUMO energy gap. And that energy gap tells us if the compound is stable or if it's not stable. Now, the larger the energy gap, the more stable the compound is. And the lower energy gap, the less stable the compound is. But the less stable the compound is, the more reactive it will be. So let's see, let's compare them. And the formula for that is E LUMO minus E HOMO. So this minus this, okay. So this is the energy gap. You can see this. Now looking at these results, let me highlight this. Now you can see that the energy gap for methanol is 9.25, while the energy gap for formaldehyde is 6.16. And like I told you, the larger the energy gap, the more stable the compound is. So this also tells us that methanol is more stable than formaldehyde. However, it also implies that formaldehyde is more reactive than methanol. So that's one information you can often get from carrying out the DFT of molecules. You can use HOMO-LUMO energy to obtain the energy gap. You can also obtain things like chemical hardness, chemical potential, but we'll not be doing that today. Next time we'll find a way of also incorporating that. So first of all, like I told you, DFT helps us to calculate the energies of systems. So the first thing we did was we carried out optimization using the molecular mechanics. Then we now carried out the density functional theory method, and then we calculated the HOMO-LUMO energies, and that's what gave us what we have here. So from this you can clearly see that methanol is more stable than formaldehyde. Also, that implies that formaldehyde is more reactive than methanol. If you also want to carry out a visualization, you can simply click on this and you can see different visualizations. This for LUMO and then this is for HOMO. Okay, so there's it. So you can see, and often you will find this in a lot of journals. You can easily snap this and then use it to explain your results. Next time, we'll also go ahead to explain the significance of all of this. But today, I've been able to introduce you to how to carry out DFT studies of small molecules. Thank you for listening. Please don't forget to subscribe to this YouTube channel. Thank you. Bye bye.